Transport Engineering and Surveying Video Lecture 6B, Horizontal Alignment of Transport Links. In the lecture I covered a lot of the theory behind horizontal alignment, looked at camber crossfall super elevation, looked at deriving the minimum radii. I'm not going to go through that, I'm just going to do some examples. So you do need to look at the lecture notes for 6A, make sure you're happy with them in order to be able to follow what I'm going to be covering in this video lecture. So we'll start off looking at an example. We've got two straight S2 rural roads that are intersecting at an angle of 30 degrees, and we need to connect them with a circular curve. We've decided that we're going to use a super elevation of 5%, and we have to determine the minimum radius of the circular curve and the length of the circular arc. So we know that the first straight road is coming in here, the second straight road is coming in here. If we project these two lines, we can work out the intersection angle and work out the circular curve that will fit best between those two roads. T1 and T2 are the tangent points. So this is where the road first starts to deviate from being a straight road to being the circular curved road. Now quite clearly you could have let's get a pen, you could have a very, very small curve, or you could have a much bigger curve. And what dictates that is the road speed, pretty much. So a faster road speed would require a bigger curve like this. Don't know where that's gone. Put it back. Fast road. Whereas if you had a very slow road, you could get away with quite small curvature. Let's have a look and work through this problem. It's the one I did in the class, and then I'll move on to another example. Okay, so all the information is in the question. We know it's an S2 rural road. That's a single carriageway road. Therefore we can work out what the national speed limit is. We're asked to find the minimum radius of the circular curve and the length of the circular arc at these three different speed limits. And we're given information including the intersection angle, which is 30 degrees. We know that the super elevation of the road is going to be 5 degrees, which is the normal amount. That's enough information to get started. So first of all, let's look at the national speed limit. Now, it's an S2 road, single carriageway, therefore the national speed limit is 60 miles per hour. Which means the design speed is 100 kilometers per hour. So this is different from what I said in the lecture. I think in the lecture I used the absolute conversion. So I went for 96 kilometers per hour. It should be 100. Someone pointed out in the lecture, and they were right. So we use a design speed of 100 kilometers per hour. If we know the design speed of 100 kilometers per hour and we know the super elevation, which is 5%, we can work out what our minimum radius is. Uh, 720 meters. And once you've got that, we can calculate the arc length between T1 and T2. That's equal to the deflection angle multiplied by the radius times pi over 180. So that is 30 multiplied by the radius of 720 times pi divided by 180. So the arc length for the national speed limit is 377 metres. For 50 miles per hour, design speed is 85 kilometres per hour. Therefore, R min is 510. And the arc length is 30 by 510 by pi over 180. And we get 267 metres. For the 40 mile an hour speed limit, design speed is 70 kph. Minimum radius is 360. And the arc length is going to be equal to 30 multiplied by 360 times pi divided by 180. I've got 188 metres. So you can see that as the speed is decreasing, not only is our radius decreasing, our arc length is also decreasing, which just makes geometric sense. If you were to draw them on here, we haven't got a scale, but you can certainly draw the relative arc lengths. Just redraw that one up there. So you've got a very small arc length, slightly bigger, depending on the speed limit. So as you can see, the design process is, once you've got the DMRB, the Design Manual for Roads and Bridges, which gives you all these values, all these tables, as long as you understand what the process is, it's fairly straightforward. Okay, let's look at another example. So a really similar, really quick example. This time we've only got to worry about 40 mile an hour. Let's change pen. We've got a super elevation of 5, therefore design speed of 70 kph. If we've got 70 kph and we've got 5% elevation, minimum radius is 360 metres. And that's a minimum radius. If we also wanted to find the arc length, which it doesn't ask for, but let's do it anyway. And we multiply the intersection angle by the radius by pi over 180. That's just to convert it. And that arc length is 282. That's 6.3 metres. So let's look at some stopping sight distance examples. Once you've got the tables, these are also pretty simple. That's just an equation you need to know, and that will be given to you when you need it. So in this case, we've got an S2 road, simple carriageway. We've got a design speed of 85 km per hour, curve radius of 600, so radius is given. We need to determine the required distance to be kept clear of obstructions, and that is because quite clearly we need to keep this zone here clear, because if there's a car coming in this direction, he wants to have a good window of visibility all the way around the curve, as far around the curve as he needs in order to stop safely. So that's what we're looking at the moment. Now the equation, MS, is the term we use to define the unobstructed verge width. MS is equal to R 1 minus cos 28.65 times the stopping distance divided by R. Those in the square brackets actually, keep it more distinct. So this example, we can just put this straight in, we've got all the information. So MS, curve radius is 600, 1 minus cos 28.65. Stopping distance we need to read off. So our design speed is 85. Let's use the desirable minimum of 160. So 160 divided by 600. And we can calculate that as 5.33 metres that need to be kept clear of obstruction. So from the edge of the carriageway, we need to make sure that we maintain a low profile, 5.33 metres, throughout the duration of that curve. And that is to give the drivers a good enough viewing angle so they can see far enough ahead. So we'll do a similar example. We've got a D2M road at the national speed limit. You should know that D2M is a dual carriageway motorway. Super elevation of 7% allows us to really reduce that radius of curvature. If this road is curving at the maximum permitted rate, how big does the unobstructed verge need to be? Okay. So D2M therefore the design speed is 120 kilometers per hour. 120 kilometers per hour, desirable minimum, stopping distance is 295 meters. MS is going to be equal to the radius of curvature, 1 minus cos 28.65 times the stopping distance divided by R. So we need to determine what that radius is. It's just saying the road is curving at the maximum permitted rate. So we've got the design curve table. We know that we've got a design speed of 120 because it's a D2M. We know that we've got super elevation of 7%, which is quite high. So our horizontal radius, our minimum radius, is going to be 720 meters. So put all that into the equation. We've got 720, 1 minus cos 28.65 times 295 divided by 720. Into the calculator. And we get a verge width that is rather large, 15.06 meters, which need to be kept clear of obstructions. In reality, what that means is a low profile, so So normally grass, but maintain that grass, cut it down, make sure bushes don't grow, make sure plants don't grow. Certainly above a height of about 1 metre, so that the drivers have that visibility all the way around the curve.